Hello everybody, my name is Glenn Berry and I'm the owner of Dr. DMV LLC, and this is Building a Home Computer Lab. Before we jump right in the presentation, you should think about exploring what PASS has to offer. That includes things like SQL Saturdays, local user groups, and virtual groups, and of course the PASS Virtual Summit this year. Please make sure to fill out your session evaluation before November 20th so you might be able to win a prize. Seriously, your feedback is very important to me and to the PASS Summit. So I'm Glenn Berry, the owner of Dr. DMV LLC. All my contact information is here on the screen, including my LinkedIn, my Twitter, and my email. And also this has some information about my blog entries and my books that I've written, and finally my YouTube channel, so please check that out. So I know how to brew beer. I've been brewing beer for about 5 years now. It's a fun hobby, and it's all grain batches using that system you see right there. So I also have 2 miniature Dachshund puppies. They're both a lot of fun. The black and tan one is named Chorizo, and the other one is named Andouille. So we have a sausage theme for the dogs. So what are we going to talk about in this session? Well, what is the purpose of your lab? And we're going to talk about the requirements that you might have for your lab and what constraints you have for your lab. And then talk about compute and capacity limits for different kinds of systems you might decide to build, and then talk about some key points in building a system, and then how to avoid some common build mistakes, and how to optimize your system after you've built it. So we've got a lot to cover. So one of the first things you need to think about is what kind of a workload are you going to have for your home lab? Because that's going to drive a lot of your choices and decisions. You need to think about what is your main use case for this lab. And of course, you might have more than one use case, but think about what your most important one is. So maybe it's running SQL Server 2019 on a bare metal machine. That's a fairly simple use case. Or you might want to run multiple versions of SQL Server on one machine. Or maybe you're interested in running multiple virtual machines on one bare metal machine. You might be interested in playing around with Docker and containers or doing video rendering work. So whatever it is, think about it in advance before you decide what you're going to do in the end as you build this lab. Here's a screenshot of Task Manager running Camtasia 2020 during a rendering run of a video. And you can see what's happening to my CPUs and GPUs here. So it's just one example of what you might want to build your system to handle as best it can with the right components. Different workloads that you might be interested in running are going to have different needs. So what part of the system does your workload actually stress? Things you might be thinking about is the total CPU capacity or performance that you need to have to support your workload. You might be thinking about how much memory do you need in the system, or how much memory performance do you need to support your workload. You also might be thinking about how much storage space and how much storage performance do you need to support the workload you want to have. Another thing to think about, especially in a lab setting, is what kind of external connectivity story do you have? What kind of network do you have? What kind of external storage do you have? And how they're going to communicate across these different machines that you might have. Another thing to think about at this point is what form factor and how much noise can you tolerate and how much power usage are you willing to have for your system. For example, you might need to have a very quiet system because you live in an apartment or a smaller house and you can't have the system be very noisy. So that's something you need to think about a little bit. So what requirements do you have for your system? You want to try to estimate what your system requirements are. How much capacity and how much performance do you need or just want? So things to think about along this line is how many CPU cores and threads do you think you need? And what relative level of single-threaded CPU performance would you like to have? How much RAM would you like to have in your system? And what are the total amount of storage space and relative storage performance do you think you need? And then also, are you going to be stuck with Wi-Fi, or do you have gigabit Ethernet? Do you have 10 gigabit Ethernet in your lab? And do you have any kind of external storage such as a NAS or external drives that might be using Thunderbolt storage or just different levels of USB storage? So things along this line is what you also need to think about as you're thinking about what kind of a system that you want to build here. What constraints do you have on this lab? So for example, you need to be realistic about what constraints you have in place because you probably have to make some choices. Common constraints you might have is your budget. If you've only got $500 to spend, that's going to really constrain what you're going to be able to do. And also your form factor. If you have not very much space available, you're not going to be able to have a bunch of rack mount servers or a bunch of tower machines. Also, noise is another really important one. You need to think about what your partner is willing to tolerate in terms of noise and what you're willing to tolerate. And then how much power will this system or systems be using? And how much electrical capacity do you have on one circuit? So for example, if you're thinking about setting up a lab down in your basement and your basement's not finished, you might only have one or two 15 amp circuits down there, and it's going to constrain how many machines you can have running on one circuit. So think about this and be realistic about what you need to sacrifice. One thing I think is really important is to consider and measure the power usage of the machines that you have already and any machine you're going to build, because the component choices you make are going to have a direct effect on your power usage. So what GPU you pick, what CPU you pick, the motherboard and the type of storage, all that's going to have an effect on your power usage. And you can also affect that by what kind of a power supply you actually buy. So an 80 plus bronze versus an 80 plus titanium, it's going to have an effect on how much power a system's going to use. And it's also important to think about turning off your lab systems if you're not using them. A lot of people just leave them running 24/7, and if you're not actually doing anything, that wastes a lot of electrical power, and that's going to drive up your electric bill, and also you're going to be emitting more carbon than you really need to. So turn it off if you're not using the system. Some common trade-offs to think about is, again, what is your top priority when you're thinking about your constraints and your requirements? Maybe budget is your main priority, or maybe you're more worried about having enough capacity and performance to support a certain workload. And again, the form factor of your system, whether it's a laptop or an Intel NUC system or a bunch of tower PCs or rack mount servers, versus how much noise they make versus how much capacity they have. And thinking about how much capacity you want to have versus how much power they're going to use to have multiple systems. So for example, a lot of people have come to me on Twitter and said, hey, I'd like to have 256 gigs of RAM and an Intel NUC. And unfortunately, that's just not possible. You can't do that. Or maybe you want to have a rack mount server sitting in your living room, and that's probably not going to be very popular with the rest of your family. Think about what's really important to you and what you have to do to make this all work for you and anybody you might be living with at home. Compute and capacity limits, things you need to think about there. Available form factors. You're going to have different compute and capacity limits that you can use or go up to with the different common form factors that are available. For example, if you're thinking about using a laptop for your home computer lab, maybe it's a new laptop or a used laptop you have laying around, well, what size laptop it is going to have an effect on how big it is and how much it weighs, and then how much RAM and how many CPU cores it's going to have available. If you have an Intel NUC, that's a very small form factor that's popular for home computer labs, so they have quite a few trade-offs if you go with an Intel NUC or some other competitor's version of a NUC. A very popular choice that I like, that I'm going to kind of focus on for this session, is a desktop system. So there's different case sizes and different motherboard sizes that are available. They're going to affect things like how many RAM slots you have, and what kind of a CPU you can run, and how many drive bays you have inside of it. And then another choice that some people will go with is a rack mount server. And you need to think about how many sockets and how many rack units you have in that rack mount server. So let's dive a little bit more deeply into these different form factors. So one popular choice is a laptop. And with laptops, your available compute and capacity really depends on the size and the cost of the machine and how old it is. So you've got two main categories. You've got thin and light laptops, and you've got what I call desktop replacement laptops that are usually much larger. Now with thin and light laptops, usually it's a U-class mobile CPU that has lower power usage, and you only have two memory slots and usually just one drive bay. And depending on the age of the laptop, it could be a SATA drive, or a newer laptop's going to probably have one M.2 drive bay. And so typically these sorts of laptops have a 4-core, 8-thread, low-power mobile CPU, and they're limited to 64 gigs of RAM with newer machines. Older machines might be 32 gigs or even 16 gigs. And then if you've got one drive bay, that means the most you can possibly have is 8 terabytes of internal storage. Now with desktop replacement laptops, you're going to have what's called an H-class mobile CPU that has a higher power draw, and it's going to have 4 memory slots in many cases, and up to 3 even internal drive bays. That's going to give you a lot more storage. And usually you're going to go up to 8 cores or 16 threads on the CPU, and you can go up to 128 gigs of RAM and have up to 24 terabytes of storage. So that's quite a bit. Of course, a machine with those specifications is going to be fairly expensive, but that's one possibility if you want to use a laptop for your lab. So let's take a little bit closer look at a laptop that's a desktop replacement. So here's a Dell Precision 7550, and fully loaded from their webpage, it's about $9,400. And this is 128 gigs of RAM, the top of the line discrete workstation class video card, 3 M.2 drives, 2 terabyte drives, and then the top of the line CPU that they offer for that model. So this is actually a ridiculous amount of money to pay for a home computer lab, but it shows you basically the compute and capacity limit of a desktop replacement class laptop. So more interesting and more commonly used is a NUC. And NUC stands for Next Unit of Computing. And so there's 2 different main categories of NUCs. You've got a standard NUC that many people might have seen or used, and then you have newer extreme NUCs. So the standard NUC is going to have a U-class mobile CPU that doesn't use that much power, and it's got to have 2 memory slots and then 2 drive bays. It'll be a SATA drive bay and an M.2 drive bay, and you're going to have up to a 6-core, 12-thread CPU and up to 64 gigs of RAM because of the 2 memory slots, and then up to 16 terabytes of storage. And then you have an extreme Intel NUC, and that's going to be an H-class mobile CPU that uses a little bit more power. You're still limited to 2 memory slots, but you're going to have 3 drive bays and also a PCIe slot, so you can put a more of a desktop class graphics card in there. And you're going to have up to 8 cores and 16 threads on your CPU. You're still limited to 64 gigs of RAM, and you can have up to 24 terabytes of internal storage with that sort of a machine. So here's some more details about that. A standard Intel NUC might look like this. And this is the model number that we're talking about right here. And the bare bones kit for this is $959. And what you get with that is essentially that box, and then the CPU is soldered onto the motherboard, and you've got to supply your own memory and storage. So you have to buy 64 gigs of RAM, for example, and an M.2 drive, and then a SATA SSD. And you can see how big it is. It's 117 millimeters by 112 millimeters, so it's about 4 inches by 5 inches roughly, and it's about 2 inches tall. So these are very small, and they're quiet, and they don't use very much power. So you can have a whole bunch of these and not take up very much space or power, and they're going to be fairly quiet. A more extreme example of this is an extreme Intel NUC, and this is a Ghost Canyon NUC, and the bare bones kit for this is $1,439, and this gets you up to an 8-core, 16-thread, higher power usage CPU, and this is quite a bit bigger. You can see it's roughly twice as large and twice as thick, and you've still got to buy RAM and your storage and a discrete graphics card if you want one. It has integrated graphics on that particular CPU. So this is, again, a fairly expensive solution that gives you a little bit more total compute capacity than you get with a regular Intel NUC. So moving on, desktop machines. What are the limits for desktop machines? And this depends on the category of the desktop machine and which CPU vendor we're talking about, whether it's AMD or Intel. So you've got 2 main categories here. You've got a mainstream desktop, and you've got a high-end desktop, HEDT. So with mainstream desktops, you're going to have 4 DIMM slots, unless you have a really small motherboard where it might be limited to 2 DIMM slots. But most desktop mainstream machines have 4 memory slots. And with AMD, you can have up to a 16-core 32-thread processor with PCIe 4.0 support. With Intel, you're limited to 10 cores and 20 threads with PCIe Gen 3. And both of these, whether it's AMD or Intel, as long as you've got 4 memory slots, are limited to 128 gigs of RAM. Now, if you step up to an HEDT, high-end desktop, you're going to have 8 memory slots. And with AMD, you can go all the way up to 64 cores and 128 threads with a top-of-the-line Threadripper. You get PCIe 4.0 support. And with Intel, you're limited to 18 cores and 36 threads and PCIe 3.0. Now, both of these will support 256 gigs of RAM. And again, you're limited by 32 gig DIMMs for desktop consumer machines. So it just comes down to how many slots you have available. So that's an example of the desktop compute and capacity limits. Now, desktop system motherboard size is another thing you need to think about, because if you want a really small case because you have not very much available space in your house or apartment, then you have different choices here. And if you want a mini ITX, which is the smallest commonly available form factor, it's only 170 millimeters by 170 millimeters, you're only going to have 2 DIMM slots and 1 PCIe slot. And that's going to cut down how much memory you can have and how much you can do with your PCIe slot. And usually that's going to be a discrete graphics card. Now, if you step up to micro ATX, it gets a little bit larger, and usually you're going to have 4 DIMM slots and usually more than 1 PCIe expansion slot. Then if you go to ATX, which is the most common size, then it gets slightly larger, and this is going to have either 4 or 8 DIMM slots depending on what kind of a motherboard we're talking about, whether it's mainstream or high-end desktop, and then you're going to have multiple PCIe slots. And then finally, you have extended ATX, which is even larger, and usually that's used for HEDT systems. But if it's not, it might just be a regular mainstream system, so you could have 4 or 8 DIMM slots, and then multiple PCIe slots that you have to work with there. So let's take a look at what's possible with the server form factor, especially for a 2-socket server. Servers, if you're thinking about buying a brand new server for use in your home computer lab, you could go with an Intel-based server or an AMD-based server. Intel-based servers, an example might be a Dell PowerEdge R740. That's a 2-socket, 2-rack unit server. And if you did that, you could go up to 56 cores and 112 threads in the system and 3 terabytes of RAM. Now, if you went out and bought Intel Optane DC persistent memory and combine that with your regular DRAM, you go all the way to 7.68 terabytes of total memory, combining the two. Now, an AMD-based system might be a Dell PowerEdge R7525. And that thing can have up to 128 cores and 256 threads in a 2-socket system and up to 4 terabytes of RAM. And of course, most people are not going to go out and buy brand new 2-socket servers for their home computer lab, but this is what's possible. What's more common is you might go out and buy a used server that's 2 or 3 generations old that's very inexpensive. So you're going to have lower limits for memory and for total CPU cores, and also for number of PCIe lanes, for example. So here's an example of a 2-socket Dell PowerEdge R7525. And in this case, it's got 2 second-generation AMD EPYC processors that it can support, and each one can have up to 64 physical cores. And then you can see how much memory it can support, 4 terabytes. You can have a lot of drive bays in that particular model server. So that's sort of the top of the line for a 2-socket server. Now, here's sort of a summary of the compute and capacity limits for these different form factors that I've talked about. Starting at the top, we've got a thin and light laptop that might be 13 or 14 inches and weigh maybe 3 to 4 pounds. And you're going to have 4 cores and 8 threads, and it's going to be a U-class mobile CPU, and you're limited to 64 gigs of RAM. And this is for a brand new top-of-the-line machine. An older machine might only have 2 cores and 4 threads, and you might be limited to only 32 gigs of RAM or even 16 gigs of RAM in some cases. Now, a desktop replacement laptop that's typically going to be 15 to 17 inches and weigh anywhere from 5 to 8 pounds, that's going to have an 8-core, 16-thread CPU at the top of the line. It's an H-class mobile CPU, and you're going to have up to 128 gigs of RAM because most of those machines will have 4 memory slots instead of only 2. Then you go to a standard NUC, and that's going to be limited to 6 cores, 12 threads, U-class mobile CPU, and 64 gigs of RAM. Moving up to an extreme NUC, you've got 8 cores and 16 threads, an H-class mobile CPU, and 64 gigs of RAM because, again, you only have 2 memory slots. Then you go to mainstream desktop, and here it depends if you go with AMD or Intel. AMD has 16 cores and 32 threads, and Intel can go to 10 cores and 20 threads, and then both can go up to 128 gigs of RAM. And then a high-end desktop, HEDT, can go to 64 cores and 128 threads with AMD with their 3rd generation Threadripper. And then you can go Intel, stops at 18 cores and 36 threads. Both of those can go to 256 gigs. And then finally, a new current generation 2-socket server. AMD can do 128 cores, 256 threads. Intel can only do 56 cores and 112 threads. And then you have anywhere from 3 to 4 terabytes of RAM, depending on what kind of memory you're using and what vendor it is. All right, so actually building a desktop system, because that's what I want to focus on for the rest of this session. You've got 7 core components in the system. So that includes the CPU and CPU cooler, the motherboard, a GPU if you don't use integrated graphics, and then memory and some sort of storage, and then a case and a power supply. So those are the 7 core components that you have to think about and actually purchase to build a desktop system. Now, component choices, the requirements and constraints that we've been talking about so far should drive your choices here. So if you want to run multiple concurrent VMs, for example, that means you want to have a lot of RAM and lots of cores to work with. And then you want to have enough performance and space from a storage point of view to host all the virtual hard drives for all those VMs. So that's what you want to be thinking about. Now, if you want to minimize your budget, build a system for the least amount possible, think about finding open box specials or used components, and thinking about making some trade-offs with lower-end components. So maybe you decide to use a SATA SSD instead of an M.2, or even a hard drive instead of an SSD, and possibly upgrade later. And a lot of lab systems don't have GPU-dependent workloads, so you can save money by picking a much lower-end GPU or even using integrated graphics if your processor has that. So that's one way to save money on your component choices. Now, you got to think about, do I want an AMD-based system or an Intel-based system? And you probably can tell by what I've been saying so far what I'm going to pick, but AMD has certain advantages and Intel has some advantages. AMD has higher core counts and better multi-threaded performance, both with their mainstream systems and their HEDT systems. They're going to have better single-threaded performance with the Zen 2 processors that were just introduced. And then you're going to have PCIe Gen 4 support, and you've got much more powerful HED desktop SKUs. So the high-end Threadrippers have a lot more CPU horsepower than anything that Intel offers in this space. Now, Intel really doesn't have that many advantages. I had to think about it for a little bit, but most Intel mainstream desktop CPUs have integrated graphics. And if you are not going to have a GPU-dependent workload, you don't really need a discrete video card. And so the ability to run off the integrated graphics for your lab machine is a way to save some money. And then Coffee Lake and newer Intel CPUs have slightly better single-threaded performance than AMD Zen 2 and older CPUs. So if you're looking at Zen 2 and older versus Intel Coffee Lake and newer, Intel has better single-threaded performance. So that's one advantage for Intel. Here's one reason why a lot of enthusiasts such as myself are really down on Intel. And if you look here, what this table is showing you is the mainstream desktop flagship core counts that were available with different generations going back to 2011. And back in 2011, you get a Core i7 2600X that had 4 cores and 8 threads. And that was the top of the line, most cores you could get. And that was in 2011. That was Sandy Bridge. And then in 2012, they had the i7 3770K, which still only had 4 cores and 8 threads. There was no expansion there in terms of core count and thread count. And the reason for that was that Intel had absolutely no competition from AMD. The AMD desktop processors of this era were just terrible. They could not compete at all with Intel. And so Intel just sat on 4 core, 8 threads as the best you could possibly get for a mainstream desktop. So then they did it again in 2013 with Haswell. And then in 2015 with Skylake, they still had 4 cores and 8 threads. They had an absolute monopoly on the desktop. And then finally in 2017, they did Kaby Lake, the Core i7 7700K, and that still only had 4 cores and 8 threads. And that was the best you could get from Intel in a mainstream platform. And enthusiasts and regular computer users were getting tired of this over the years. And then finally, what happened in 2017, AMD released their first generation Zen desktop processors. And they went up to 8 cores and 16 threads for just slightly more money than what Intel was selling a 4-core, 8-thread CPU for. So then finally, in 2018, Intel started reacting. They had to. So they had the Core i7 8700K with 6 cores and 12 threads. And then they went to 8 cores and 16 threads in 2019. And then finally, in early 2020, they went to 10 cores and 20 threads. And that's the highest core count you can get from Intel. And AMD back in 2019 went to 16 cores and 32 threads as their top of the line. So there's a big gap there in what you can do in a mainstream system if you look at AMD versus Intel. Building a mainstream AMD desktop. This is a very popular and relatively affordable and very flexible option that I really like. And AMD AM4, socket AM4 CPUs go all the way from 4-core 8-thread all the way to 16-core 32-thread in the same types of motherboards. And the cost of those processors go from about $120 for the bottom of the line up to about $800 for the top of the line Zen 3 16-core 32-thread model. And both the Zen 2 and the Zen 3 processors will work in modern 500 series AMD motherboards. So what this means is you can use an AMD X570 or an AMD B550 motherboard, and both of those have PCIe version 4.0 support. You only get it from the CPU and not the chipset with B550. B550 is supposed to be more affordable than X570, and it doesn't have a chipset fan like X570 does, so a lot of people prefer it because of that reason. So here's an example of an AMD X570 chipset, what it looks like. And this shows you how many PCIe lanes you have to work with, and they're all Gen 4. And on the left is what's coming from the CPU, and on the right is what's coming from the X570 chipset. And this is their high-end mainstream desktop chipset that a lot of the higher end AMD motherboards will have. And you can pick this and have a little bit more flexibility and PCIe 4.0 from the chipset and from the CPU. The downside to X570 is it's more expensive, plus almost all X570 motherboards have a chipset fan that can fail, and it also generates more noise in the system. So a lot of people don't like that. But that's the top of the line chipset choice. The next chipset you might want to look at is the B550, and that is actually newer than X570. It's meant to be more of a budget choice, and it gives you the same number of PCIe lanes from the CPU, and they're Gen 4 instead of Gen 3, And then the chipset is limited to PCIe 3, but it lets you do things like have M.2 SSDs off of the chipset that are Gen 3 and not Gen 4. And the cost for this motherboard is usually going to be a little bit less than for an X570. And I really like B550, by the way. It's a good choice for a lab system. And then you have the budget choice, which is even newer. It's the A520 chipset. And this gives you only Gen 3 PCIe support. And there's no Gen 4 whatsoever here. And these are not that much less money than B550. So personally, I would avoid an A520 chipset-based motherboard. Go with B550 or X570. Here is what it looks like. This is a photo that I took of an AMD Ryzen 9 3950X mounted in a motherboard, and it doesn't have the CPU cooler mounted yet. And those little curved brackets on either side of the CPU are where we're going to mount an aftermarket CPU cooler on this particular system. And this is actually the system I'm using to record this with. It's a ASRock X570 Creator motherboard that you can kind of see upside down on the motherboard there. Here's another example of an AMD Ryzen 5 3600 in a different motherboard. It's a B550 Aorus Master motherboard, and this has the same kind of CPU cooler mounting bracket set up and ready to go. And this is a lower end. It's only 6 cores and 12 threads, but this is a very popular CPU that I think is a great choice for a lot of people who are thinking about building a system, because you could build a system using this CPU now, and then later you could upgrade it to a higher core count CPU from the same generation, or you could go to a CPU from the Ryzen 5000 series. So what we have here is the new AMD Ryzen 5000 series SKUs that were introduced and available for sale on November the 5th. And we've got 4 SKUs available here. And this is the latest and greatest Zen 3 processors for the desktop from AMD. And starting at the top, you've got the Ryzen 9 5950X that has 16 cores and 32 threads. And the base clock is 3.4 gigahertz, and the boost clock is 4.9 gigahertz. And the retail price for this is $800. And we don't know yet what's going to happen with pricing. It might be a little bit above that to begin with, but hopefully it'll go back down to the regular retail price. And this is the top of the line mainstream desktop. And what's nice about Zen 3 compared to Zen 2 is we're seeing about 20 to 25% better single-threaded performance. And so that's going to be a pretty noticeable jump if you already have a Zen 2 processor. And then you've got a 12-core, 24-thread model, the Ryzen 9 5900X, and that's actually probably the best choice in terms of bang for buck, because the price is quite a bit lower, and you're only giving up 4 cores to have a big price reduction. And this actually is the lowest price per core of any of these SKUs. And then you have the 8-core 16-thread model, the Ryzen 7 5800X. And then you've got a Ryzen 5 5600X at the bottom here. And all of these have the same Zen 3 architecture. They just have different base and boost clock speeds, and of course different pricing. And these are $50 more expensive than the equivalent Zen 2 processors were when they were first introduced. So they've increased their prices a little bit, but probably what will happen over time is pricing will go down and be a little bit lower than it is for these retail prices. So here's the older Ryzen 3000 series SKUs. These are Zen 2. And they have a lot more SKUs here because they introduce more over time. And this is what a lot of people are going to be buying still. And so you go from the top of the line Ryzen 9 3950X with 16 cores all the way down to the Ryzen 3 3100 with only 4 cores and 8 threads. And you can see the pricing on this. And the pricing jumps around at Micro Center on a daily basis. So this was from a few weeks ago, but this just gives you an idea of what these things cost for the different core counts and the different SKUs. And the difference here, in case you're kind of wondering, is you have the X SKUs. So if you see an X at the end of the model name, that means that it has a slightly higher clock speed for both base and boost clock. And then the non-X ones are a little bit lower clock speed, but they don't use as much power typically, and they're less expensive. So you have different choices here at the different core counts. So you can go 4-core 8-thread, 6-core 12-thread, jump up to 8-core 16-thread, and a couple choices with 12 cores, and then one at 16 cores. And then finally the XT SKUs, those were introduced late in the Zen 2 cycle, and they just have slightly higher boost clock speeds, and they're really not a great deal from a financial perspective, but if you don't care about spending 20 or 30 or 40 more dollars to get a little more performance, they could be a good choice. So that's the Ryzen 3000 series. So the next component to think about is a CPU cooler. And I think that air cooling is the best choice for a lab PC or for just many people's personal desktop PC, because air cooling is less expensive than liquid cooling, and it makes it easier to build the system with an air-cooled CPU cooler. And you also get better long-term reliability because liquid-cooled CPU coolers can leak. They don't do it very often, but it's possible. And then if they're really old, like say 5 or 6 years old, the liquid inside of the system starts to permeate into the hoses, be missing a little bit of that liquid over time, and they're going to fail at some point. And you don't have that problem with an air cooler. The only possible thing that can happen to an air cooler is that the fan might fail, and you could replace it if that happens, but you're not going to have the same kind of reliability problems. Quality third-party CPU coolers instead of the stock CPU cooler lets you have lower CPU temperatures both at idle and under a load. And with lower CPU temperatures, you get higher boost clock speeds. And then usually third-party CPU coolers have lower noise levels because they have better quality fans, larger diameter fans, and you can go in and tune the fans with a fan curve so that they're very quiet unless the CPU gets really hot, and then they spin up to a higher speed. So I'm a big fan of air coolers instead of liquid coolers for CPU coolers. So here's an example of an MSI B550 Tomahawk motherboard, and this is a pretty good choice for a lab system. If you look closely here, you can see that it's got 4 DIMM slots and it's got 2 M.2 slots. And only one of them is Gen 4, the one closest to the CPU, the one that says Lightning Gen 4. The one at the bottom is only Gen 3. And that's what you're going to see on most B550 motherboards. There's a few exceptions where they route some of them directly to the CPU instead of going through the chipset. But anyways, this is a nice system, or a nice motherboard, I should say, because it's got extremely large heat sinks for the voltage regulator modules to the left and above the CPU socket. And that's important when you're looking at overall motherboard quality, because if you're running under a heavy load with a high core count CPU, those VRMs start to get really hot. And if they get hot enough, it can cause everything to get so hot that you start to see thermal throttling of the system, and you don't want that. Here's an example of what I was talking about. Hardware Unboxed, which is a very good YouTube channel based out of Australia. This is a screenshot from one of their videos that's showing some thermal testing of voltage regulator modules. And you can see different model motherboards on the left, and you can see what happened after they ran Blender, which is a multi-core workload, for an hour. And the room temperature was 21 degrees C, and then they measured the temperature of the VRM after that torture for 1 hour. And you want to be lower here. So the Gigabyte B550 Aorus Master is only 37 degrees, whereas the one at the very bottom, an Asus Prime B550MA, was 103 degrees. A huge difference there. If you're thinking about buying a motherboard to build your system with, looking at resources like this that show you which ones do a better job of keeping the voltage regulator module cool is a really good idea. That helps you pick a good quality motherboard, because there's so many different motherboard models, somewhat overwhelming to pick a good one. This is one thing to look at. So here's an example of a discrete GPU. And as I said earlier, GPUs are not usually stressed with most lab workloads. If you're running SQL Server or running VMs that are running SQL Server, that's not going to be punishing your GPU very much. And you don't need to go out and buy a really expensive top-of-the-line discrete GPU. You can even get away with integrated graphics if your CPU offers it. Getting a high-end GPU is going to be expensive, and it's also going to use a lot of power, which might cause you to actually have to buy a bigger power supply than you otherwise would need. So I think you want to pick a good mid-range GPU if you're not quite sure how much GPU you might be using. And a GTX 1650 Super or stepping up to a GTX 1660 Super are both good choices that are not that much money, that give you plenty of horsepower to run almost any kind of a lab system. Now, one exception, if you know you're going to do things like rendering videos that actually use your GPU, then you might want to get a more expensive GPU. But if you're just running SQL Server, something like this is more than adequate for that. So here's an example of memory speed and why it's important. Because a lot of people will go in and look at the spec sheet for a motherboard on somebody's website like MSI, and they'll see that, oh, they offer up to 5,000 DDR4 5000 support on this CPU. Does that mean I need to go out and buy DDR4 5000 RAM? No, you don't need to do that. And that would be a waste of money if you did that. It's going to be extremely expensive, and you're really not going to see much performance benefit, and you're actually going to take a hit in many cases, because with Zen 2 AMD processors, once you go above about 3733, what happens is the Infinity Fabric speed gets cut in half. So instead of going the same speed as the RAM, it runs at half speed. So what you want to do is pick memory that is DDR4 3600 or DDR4 3200. That's sort of the sweet spot, and that's not very expensive, and you're going to get the best performance for your memory and still run your Infinity Fabric at the total same speed as your memory speed. So again, as you see in this slide, they're recommending DDR4 3600 with CL16 timings is kind of the best price performance configuration for your memory. And Zen 2 makes it easy to run that kind of memory. Zen 3 has even better memory support, so I can't wait to actually get one of those for one of my systems. So here's an example of what DDR4 3600 memory looks like. And as I said before, don't overspend on your memory. You don't need to go out and get DDR4 4000 or DDR4 5000 memory. You want to stick with DDR4 3600 or DDR4 3200, and you want to get 2 or 4 sticks of RAM instead of just 1 or 3, because that lets you use dual channel mode for your memory, which really increases the bandwidth of the memory. And I think it's a good idea to start with 2 sticks and then favor larger capacity sizes. So don't get 4 gig or 8 gig sticks of memory. Get 16 gig or 32 gig sticks and just get 2 of them to start with. And then you'll have 2 empty slots. And if you need more memory later, you can get 2 more large capacity and potentially max out your motherboard, which would be 128 gigs with 4 32 gig DIMMs. So that's how you want to look at it for a lab machine. So moving on to storage, I really like M.2 storage. I really want to have that if possible for my boot drive. This is the largest capacity of this particular model. It's a Samsung 970 EVO Plus, and TLC stands for triple level cells of NAND, and that's not as good as MLC, but you just don't see MLC very much. And what you're seeing a lot of nowadays is QLC, quad level cell. Samsung SSDs are slightly more expensive than some other brands, but they're very reliable. They're very easy to work with, and I like them. But if you want to save some money, you can go with a different brand that might be a little bit less expensive than Samsung. So this is a 2 terabyte Samsung 970 EVO Plus. That's one of the better Gen 3 M.2 drives. Here's a brand new model from Samsung, the 980 Pro. And this is also TLC, and it's an M.2 drive. And Right now, the largest capacity you can buy is 1 terabyte of that, but they're going to have a 2 terabyte in the future. And so if your system supports Gen 4, you could use one of these. And the main advantage of Gen 4 is that it doubles the bandwidth compared to Gen 3. And also, usually they have better controllers, so you might get more IOPS out of one of these. But to be honest, Gen 4 is not going to make a huge difference for things like how long it takes to boot your system, but it's going to make a big difference if you're doing things like running a SQL Server backup or moving a VM virtual hard drive from one place to another. Things that depend on sequential performance, you're going to see an advantage by using a Gen 4 instead of a Gen 3, but it's not going to make things like loading Management Studio go any faster. So be aware of that. Now, if you want really high capacity, the biggest M.2 drive you're going to be able to buy right now is 8 terabytes. And Sabrent has a model called the Rocket Q. And that QLC, again, is quad level cell. And quad level is less expensive to manufacture, but it doesn't perform as well or have as much durability as TLC or MLC does. But having 8 terabytes of storage in a drive like this is about as big as a stick of gum is pretty amazing, especially if you only have one M.2 drive bay in a laptop or a Nuke, for example. Going up to 8 terabytes is a nice option that you can look into. Here's an example of a really high quality desktop tower case. This is the Lancool 2 mesh, and this is one of the highest rated cases out there right now for airflow. And when you're looking at a case for the system that you're going to buy, you shouldn't just be focused on what it looks like. And it's really important not to focus on whether it has tempered glass or RGB. You want to look at how much air can flow through the system. And there's a lot of cases out there that are a lot of times aimed at gaming that have terrible ventilation. And if you look at the case on the front and it's just a glass panel or plastic panel and there's not any kind of ventilation holes to speak of, it's usually not going to work very well for ventilation. It's just simple physics. And what's popular now, if you care about performance and keeping that case as cool as you can inside, is you want to have a mesh type case like you see here. And this has open mesh in the front and mesh in the top, and even the fold down lower side that you see folded down on the left here is mesh. And so this does very, very well in thermal performance testing by Gamers Nexus, for example. And this is a great case. It only costs about $80 to $90 depending on where you buy it from. So this is a great case. Your power supply is very important to think about. Seasonic is a great power supply manufacturer, and their power supplies tend to be more on the expensive side, but this is one of their high-end power supplies, and this particular model is completely fanless, and it's completely modular. You can see those places on the front where you would plug in the different cables, and it's nice to have a modular power supply like this because then you don't have a bunch of extra cables that you're not even using. You just plug in the cables that you actually need for your system. And having it can be completely fanless like this makes it quieter, and there's one less thing that might possibly fail. And the last thing about this particular power supply is it's titanium rated. And that means it's going to be more efficient than a platinum or a gold or a bronze rated power supply, and it's going to use less power and save you money on electricity over the life of the system. Although on the downside, a titanium power supply is usually more expensive up front. So depending on how much your electricity costs, it may take a while to pay back. Taking a look here, we have the different power supply efficiency levels that are available. And starting at the top, you've got 80 plus, and then you have 80 plus bronze, and then silver, gold, platinum, and titanium. And titanium is the highest rating here. And the important thing to keep in mind here is that you don't want to go out and get a power supply that's much bigger than you actually need for your system, because if you're only running at a 10% or 20% of your capacity, your efficiency is quite a bit lower. The sweet spot is a 50% load. So if you're only going to use 300 or 400 watts when your system is running under a load, you don't want to go out and buy a 1,000 watt or 1,200 watt power supply. You're better off with a lower capacity, and you're also better off if you get a higher efficiency rating, but they are more expensive. So here's another chart that makes this a little bit more clear. Power supply sizing. And what I'm trying to get across here is don't oversize the power supply. It's very unusual with non-gaming systems to need anything larger than 750 to 850 watts. And in fact, most systems can get away with 500 to 600 watt power supplies. Because again, you want to be at 50% of the rated capacity, and you want to get 80 plus gold or better if you can. And that chart at the right is showing different video cards and then how much power, how big the power supply needs to be with different class processors. So if you're looking at getting an RTX 3090, which is extremely expensive, by the way, it's about $1,500 for that video card, and you're going to run that in a Threadripper system, then you probably do need a 1,200 watt power supply. But most of us are going to be running something more like a Ryzen 9 or a Ryzen 7, and maybe you're running a 1660 Super like I was talking about. So if you look there, that means you can get away with a 550 watt power supply. And that's a lot less expensive than a 1,200 watt power supply. And you're going to be more efficient also because you're only going to be drawing maybe 250 to 300 watts when you're running fully loaded on the GPU and CPU. So let's take a look at what desktop systems might look like. This is actually down in my basement what my lab used to look like a few months ago with 4 desktop systems here in a little rack. And you can see I labeled them with what processor was inside of them at the time. I've upgraded all these since then, but these were all Ryzen 5 systems except for the second one from the left, which is a Ryzen 7 2700X, and I've upgraded all of those since then, but these were good choices at the time as I was experimenting with different processors and how powerful they were and how much power they actually use. Let's talk about actually building a system and avoiding some common build mistakes. A few things that I see very often when people build systems is not reading the manuals, and so in particular the motherboard manual and the manual for the case. And then it's very common to install some of the components in incorrect slots or ports. So for example, putting the video card into one of the PCIe slots that's furthest away from the CPU instead of the one next to the CPU. Or with M.2 storage, installing it in one of the slower M.2 slots instead of the fastest one that's connected to the CPU. And the same thing with SATA storage. Some of your SATA ports might have different speeds, so reading the manual will help you avoid those sorts of things. It's also very common to install the memory in the wrong slots. So you've got 4 memory slots on a mainstream motherboard, and it's important if you only have 2 memory sticks to put them in the right slots so you get dual channel mode on your memory. And then it's also very common, I found, to have people install their fans incorrectly. So the case fans and the fans on a CPU cooler, the fans on a radiator if you're doing liquid cooling, it's important that you install them in the right direction, and I'll talk more about that in a few slides. Another thing that I see people doing sometimes is not using any thermal paste between the CPU cooler and the integrated heat spreader on the CPU itself. Another common mistake is not removing the plastic cling coating that might be on your CPU cooler to protect it from being scratched. And if you leave that on there, it really affects how well it can transfer the heat from the CPU to the CPU cooler. So another thing I see fairly often that's not really a mistake is not doing any cable management whatsoever. Here's something that I like to do, and you don't have to have a special test bench to do this, but do all your assembly as much as possible on the motherboard when it's outside of the case. And you can just set it on top of your motherboard box if you don't have a test bench like this. But installing the CPU and installing the memory, installing your M.2 drive, and possibly installing your CPU cooler if it's an air cooler on the motherboard before you put it in the case is a lot easier than if you do it after you put the motherboard in the case. That way you'll save yourself a lot of hassle. And plus, if you have it set up like this, even if it's just on top of your motherboard box, you can plug in your power supply and put a video card in if you want and actually see if the system works before you install it in the case. So that's another thing you might want to do. Here's an example of what I was talking about with installing the case fans incorrectly, and they're actually set up correctly in this picture, but what you want to have happening is you want the cool air to be coming in the front of the system, which is on the right in this case. And so the fans that are on the right, the intake fans, you want to make sure they're oriented so that they're pulling the air in. And if you're putting your own case fans in, for example, a lot of people don't realize this, and they'll set them up so that they're pushing the air out instead of pulling it in. And that's not what you want. So you pull in that cool air from the front, and then it goes through the system and picks up heat from the components. And then the fan at the top left is your exhaust fan. And you also might have a fan at the top. And so you're trying to push that hotter air out the back and out the top of the case. And having the fan set up correctly to do this is actually really important if you want to have good ventilation through the case and keep your components as cool as possible. Here's an example of a completed system with fairly decent cable management. And you have on newer cases some cable management features built in, like those grommets around those holes. And if you think about what you're doing and try to route your cables as much as you can behind the motherboard on the other side of this case, then you can hide a lot of those. And that just makes it a lot cleaner. And the reason you care about this is that it improves the ventilation through the case, and it helps reduce dust buildup inside the case on the cables because they're all tucked out of the way, and it just looks nicer. It shows that you took a little bit of time to do a decent job here instead of just having a rat's nest of cables inside the case. And here's another system with a little bit nicer cable management job. And this is no means top of the line professional cable management. If you really want to go all out here, you can get cable extensions from your power supply, and you can pick what color you want them to be, and you can use cable combs and make it really beautiful. And this is just sort of bare minimum using the stock cables to try to tuck things out of the way. So try to do that if you can on a case, and especially if you have a glass side where people can see inside. So anyways, here's some blog posts that talk about this. I've got a blog post called Building a Home Computer Lab, and then another one that's talking about avoiding some PC building mistakes that people often make, and another one that talks about how do you properly orient your case fans. Moving on, optimizing your system. And there's some things you need to do, especially with an AMD-based system, to make it run as fast as possible after you build it. Some of them are hardware and some of them are software related. So let's just go ahead and start talking about that. Some steps that you want to do for an AMD Ryzen system. It's very important that you update to the latest BIOS version for your motherboard. And even if you buy a brand new motherboard from a store, it's probably been sitting on the shelf for a while and going through the delivery chain coming from Taiwan. And so it might be 2 or 3 months old when you get it. And especially if you're planning on using a Ryzen 5000 processor, you want to have the latest BIOS, or at least one new enough to fully support that processor. And if you're going to use a Ryzen 3000 series, it'll probably still work with an old BIOS, but you're going to probably be giving up some performance and some improvements, especially to memory performance. So go and check that, and then go ahead and update the BIOS. And then after you have the system built and Windows is installed, then you want to go in and enable XMP in the BIOS, which makes your DDR3 or DDR4 rather 3600 memory run at its full XMP speed instead of the JEDEC speed, which is quite a bit slower. And this is actually pretty important for AMD Ryzen processors. So at a bare minimum, do that. But if you really want to squeeze even more performance out of your system, there's a new free program out there called Clock Tuner for AMD Ryzen that you can follow this link and download that. And if you're willing to spend a little bit of time playing with that program and letting it do its magic, you can get more performance usually than just running it stock, and you can even get lower power usage. All right, so then it's important to install the latest version of Windows 10. And every 6 months, Microsoft releases a new long-term servicing version of Windows 10 that quite often has some performance improvements. You want to be on a new enough version, which is at least version 1903 or newer. That's when Microsoft and AMD worked together to make some improvements to the scheduler, and they also made some other improvements to make the processor clock up more quickly. So you get a decent performance boost just by having Windows 10 version 1903 or newer. It's also very important that you go and get the latest AMD chipset drivers. You want to get those chipset drivers and install them, and then you're going to get the best performance from the system. And it also gives you special customized power plans for AMD processors that you won't get with a stock Windows installation. Then you want to go out and go to your motherboard support site and get all the vendor-specific drivers for things like storage and network and GPU if you're using integrated graphics. And if you're not, if you've got NVIDIA discrete graphics or AMD discrete graphics, go to their website and get the GPU drivers for that. And if you have third-party storage, like say a Samsung SSD, you want to go out and get the Samsung NVMe driver that matches with your SSD. And then finally, after you've installed Windows and installed everything and patched it, you want to make sure to run Windows Disk Cleanup, because you'll probably free up a decent amount of disk space by doing that, and a lot of people never do that. Let's talk a little bit more about some of these updates. So this slide explains what you have to do to get Ryzen 5000 series processors to work with various different AMD motherboards. So as I was talking about before, if you've got an AMD 500 series motherboard, so that's B550 or X570 or even A520, you're going to have to be on a GISA version 1.1.0.0 to get the full functionality from that. And you have to be on a GISA 1.0.8.0 to even get it to post. And as I said before, if you went and bought your brand new B550 motherboard just this week, let's say, and maybe that motherboard was actually manufactured in Taiwan in early August, so it has an older BIOS version. So then you go and buy your brand new Ryzen 7 5800X processor, for example, and you install it, and your system won't even post. And that's going to be pretty frustrating if you don't have an older AMD processor to put in there. And there's a way around that. A lot of AMD motherboards have a BIOS flashback feature that lets you actually flash the BIOS with no CPU and no memory and no video card. You just have to plug it in to a power supply. And I've got a YouTube video that talks about how to do that. So the point is, you need to have a new enough BIOS version to make an AMD 500 or 5000 series CPU work, even with the latest motherboards. And then you're going to have to wait a little while if you want to stick with the older AMD 400 series, so an X470 or B450. That's going to eventually work with Ryzen 5000 series processors, but you're going to have to wait till probably January before they have a new BIOS version that'll let you run that newer processor in your older motherboard. And I'm not too sure how many people are going to actually do that. I think a lot of people who are going to get Ryzen 5000 series processors will probably go ahead and get a newer motherboard so they get PCIe 4.0 support. This is an example of going into your motherboard support site and getting the latest BIOS version. So this is a B550 Aorus Master, and it shows the different BIOS versions. And you would want to get the F11B version that's shown here at the top, and that would give you full functionality for the Ryzen 5000 processor, just like it shows there. So here's what it looks like if you go in to the motherboard setup into the BIOS. And then usually there's going to be a utility such as QFlash for gigabyte motherboards. And this is how you would update from one BIOS version to another. And you download the BIOS and stick it on a thumb drive. And then you go ahead and boot up the system and go into the BIOS setup and take care of it. Then here's an example of the latest version of Windows 10 when I'm recording this is this brand new Windows 10 October 2020 update. And so if you're running an older version of Windows 10, you would want to get on this version if you want to get the best performance and security. So it's just a good idea, in my opinion, but it's important you're at least on version 1903 to get the best performance from an AMD processor. Then here's an example of what I was talking about, where the Windows 10 May 2019 update, so as Windows 10 version 1903, has these improvements to the scheduler on the left side, and on the right side there's this thing called CPPC2 support, which means that it ramps up the clock speed in 1 to 2 milliseconds instead of roughly 30 milliseconds. So that's going to make your system a lot more responsive. If you're one of those people who you've got Windows 10, but you're on a really old build of Windows 10, you want to at least get on version 1903 if you're going to be running an AMD processor. And then this is what it looks like if you go to the AMD site and go and get the latest chipset drivers. And this is version 2.10.13.408 that was released on October 19th. And every 2 or 3 months, typically there's a new version of these. And sometimes they make big improvements here that are quite important. And unfortunately, they don't always specify all the improvements, but usually the word gets out if something is important or not. And then here's an example of going to NVIDIA. And if you've got an NVIDIA graphics card, you want to try to be on the latest version of that because performance improves and they fix bugs. If you just install Windows 10 on your system, it's going to use an older NVIDIA driver that Microsoft has access to. And it's not going to be the latest and greatest. The system will still work, but usually you're going to be giving up some performance. So the little details like this typically do make a difference. And then I've got some relevant blog posts here that talk about this in more detail. I've got 7 setup tips for a new AMD Ryzen 3000 system, and then preparing your system for Zen 3 processors, the things you need to do to make sure it's going to work with a Ryzen 5000 processor, and then checking your memory speed to make sure that you're running at XMP speeds for your processor and memory. And that's really important for performance. So I want to thank you for listening to this, and hopefully some questions have come up during the session. And if you think of something later, go ahead and reach out to me with my contact info and ask me a question about this. Hopefully you can tell that I'm really passionate about PC hardware, and that ties into server hardware, obviously, because they're using the same technologies on many levels. Again, thank you for listening to this.